Well, hey guys, Mr. D back again for a little more remote learning. The last couple classes have all been about Newton's first law, and it's time to move on and talk about Newton's second law. Okay, he's got those three laws. We're on number 2 now, and Newton's second law is, I think, one of the least understood by my students. It's one that is pretty simple, but because of the math involved sometimes can be kind of hard to wrap your mind around. So we'll take a minute today and we'll think about what Newton's first law is all about. Now the law itself, if we were going to recite it, we would say Newton's first law, it's an equation basically. It tells us that force is equal to mass times acceleration. And there's a ton of stuff we can do in physics with this, but essentially it's an equation. It says F is equal to ma. Force is equal to mass times acceleration. So there you have it. There's Newton's second law. Force is equal to mass times acceleration. So let's define the three variables in there. We've learned essentially about all three of these today this year, but we know that force is a push or pull on an object. When we talk about force, we're talking about a push or a pull on an object, and that's measured in newtons. This guy was enough of a beast that they named a unit after him. We measure force in newtons. That's pretty cool. And mass, oh, we better know what mass is at this point in the year. Mass is the amount of matter in an object. So here's the cool thing. We talked a ton this year about the difference between mass and weight. Mass is the amount of matter in an object. Weight is a measure of force. And we can calculate weight using Newton's second law, because guess what? We can figure out how much, if we go force is equal to mass times acceleration, we can figure out how much stuff is in your body. We know you're standing on Earth, so we know the acceleration due to gravity is 9.8 meters per second squared, and we can calculate the force that gravity is pulling on your body, your weight, and we would calculate that in newtons. So there's Newton's second law in action right off the bat. By calculating your own body weight, we're doing that. We're using Newton's second law. So it's the force of the amount of matter in an object is the mass, and then find the acceleration is any change in velocity. So let's just say a change in velocity is acceleration. So let's do a couple real world connections here. Let's think about the different Newton's second law in action, and I often think about things like race cars and things like that, and it's hard to isolate these laws into one example because all three of the laws are tied together so closely, and you'll see what I mean here in a second. But let's do some basic math. Let's say that we have an object we have an object with a mass of 5 grams. And we are gonna, we're not even gonna use units here. Let's just say we have an object with a mass of 5, and we're gonna multiply that by an acceleration of 2. We know that the force generated by that object, or the force needed to get an object with a mass of 5 to accelerate at 2, is going to be 10. Okay, now here's the crazy thing. So let's say we double the mass of the object. We take a really big object and we give it a mass of 10, but we want it to accelerate at the same rate. Well, guess what? The force required doubles, okay? And that's where this tractor, trailer, truck, small car example comes into play. So let's think about this. Let's go here. So tractor, trailer, truck versus small car. Here's what I'm thinking of. We've all sat at a stop sign next to a tractor, trailer, truck, and the light turns green, and if you're in a small car, you tend to zip away from that tractor, trailer, truck that takes much longer to accelerate. So let's say a big truck's acceleration, that's A in our equation, okay? A big truck's acceleration off the line is slower than a small car, and that's all Newton's second law, right? So let's note here the car's engine is much less powerful, right? If we think about the force being generated by a tiny little car's engine compared to a giant diesel tractor-trailer truck engine, there's way more force being generated by that tractor-trailer truck, but the car is so much lighter, less mass, so it's got such less mass that it actually accelerates quicker. And if you've ever watched drag races on TV, or dragsters, we think about those cars. They not only have immense power in their engines, but the car is as light as possible. Like, you look at those funny cars, essentially they're these big wheels and they're long, and they have these little wheels on the front. They got a big spoiler on them here, and there's a guy sitting in there with his helmet on right there. It's essentially just a gigantic engine with nothing else. So essentially what they've done is they've taken a huge, powerful engine, stripped off as much weight as they can to get the most acceleration out of it. And that's all Newton's second law in action, right? If we can take a massive amount of force, let's say, a force of 100, and we can get the mass really, really small. Let's get the mass down to 2. We know our acceleration is going to be 50. Right? But if our force stays the same, we take that same engine, but our car is heavier, our car has a mass of 10, all of a sudden we drop our acceleration way down to 10 in this equation. So Newton, essentially in the second law, he connected the fact that math and science are connected. They're enslaved to one another. Math is essentially the language of science. It's how we communicate all these observations we make about the universe around us. So Newton's second law is cool. It just identifies how enslaved these variables are to each other. You mess with one, you inevitably change the other. So let's think about one more example here. And this one I always use in class because you guys have all maybe played a little red dot ping pong ball in your lives here. But if we look at a golf ball and a ping pong ball, let's think about this. Let's say both are about the same size. That's volume, right? They both take up about the same amount of space. One has much less mass. So we think about this, the ping pong ball, there's nothing inside, right? It's way less massive than a golf ball, okay? And we can say the one with less mass hits with less force when accelerated at the same rate. Okay, so think about this. I always use this as an example. I'll ask a kid in class, hey, if you're being honest now and you're not being some kind of tough guy, what would you prefer if I'm going to cock back and throw one of these balls at you as hard as I can, which would you prefer I throw? And anybody with common sense says, the ping pong ball. Nobody wants to get pegged with a golf ball as hard as I could throw it, right? So we are all scientists. We all understand Newton's second law deep down inside, and we know that that object is way less massive. Therefore, it's going to hurt way less. It's going to hit me with less force. And you've ever seen somebody get pelted with a ping pong ball. It might sting for a second, but you get hit with a golf ball going at the same rate of speed, and that's really, really going to hurt. And that's all about Newton's second law. One, because one's mass, let's say the ping pong ball has a mass of 2, and that thing's accelerating at 10, it's going to hit you with a force of about 20. But if we look at, let's say the golf ball has a mass of 20 and it's accelerating at the same rate, right? We're going to look at the force hitting you at about 200. So because its mass goes up, that creates more force as well. So just interesting stuff to think about. So many real-world connections here. I think about NFL football players, for example. Big, giant, massive dudes that are able to accelerate really quickly. The amount of force required there is insane, and that's why they lift weights so much. That's why they're working on being as strong as possible. They're trying to get big, but also be crazy strong, and they do that through squats and all kinds of other stuff so that they can maximize their acceleration. And changing of direction is also an acceleration, and they're really good at that. Being big and being able to do that is really hard. So I think a lot about physics as I watch NFL and any sport, actually. So tons and tons of good examples of this. One other one I may give you would be like if you look at somebody running up and kicking a soccer ball, right? If we kick a soccer ball with our foot, that soccer ball we expect to launch off, and that would be because the soccer ball has a pretty low mass. But let's say, what if we hid a bowling ball inside the skin of a soccer ball, right? If we filled this thing with mass, and we made it a way more massive object, and somebody ran up kicking it, expecting it to be a soccer ball, you could really, really get hurt, right? Because that thing has so much more mass, it's going to apply a lot more force to your foot when you kick it, and that could create some big-time damage. So just tons of examples in the world all around us of Newton's second law. Our goal today is just to get our notes done. Save these notes. These will become very useful to you as we watch our video next class and try to apply Newton's second law to the real world around us. I can't thank you guys enough for your effort during this time of remote learning. Shoot me an email